Magus Day, everyone. Welcome to the second part of our discussion on molecular geometry and polarity. Okay, right now we are on our second learning target, which is to decide whether a molecule is polar or non-polar. Now, there are a few things that we have to remember. So, in our discussion on bond polarity, we were talking about polarity arrows, okay, or they give us the direction of where the electrons will be going, and it usually points to the direction of the more electronegative atom. So, this is actually quantitatively measured by dipole moments. So, represented by the Greek letter mu. Okay, so when you say dipole moments, these are quantitative measures of the polarity of a bond, and it is a vector quantity. Okay, that means it has a magnitude and direction, but we won't be dealing too much with the math as long as we know the concepts behind. Okay, so when you talk of molecular dipole moment, it is basically the sum or the vector sum of all bond moments. And this will be considered in determining the polarity of our molecule. Okay, so if you remember, the dipole moment is represented by the arrow, okay, the polarity arrow, which points towards the more electronegative atom, as in the case of HCl. So there's a polar bond between the hydrogen and the chlorine atom, since chlorine is way more electronegative than hydrogen. So in this area, we have a partially negative end, and in this area, we have a partially positive end, right? The yellow arrow represents the dipole moment. So in considering or in studying the molecular polarity, it actually depends on the dipole moments and how they are arranged, as well as the molecular shape. So we go back to our previous examples a while ago, wherein we talked about the molecular shape of water and carbon dioxide. So we now know that water is a bent molecule because of the presence of the non-bonding domains, two non-bonding domains present on the central atom. So what happens in here? We know that oxygen is more electronegative than hydrogen, so therefore it is hungrier for electrons than hydrogen. So there is a dipole moment in this polar bond. Okay, this is a polar bond, oxygen and hydrogen. Now, there's a dipole moment facing towards the direction of the oxygen atom, and in this same way for this hydrogen and oxygen side also. So that means there are two dipole moments and they are pointing in the same direction. So what do vectors do if they are pointing at the same direction? They add up. Okay, so there is a net dipole that is facing upward or facing towards the direction of the oxygen atom. So that means there will be a partially negative part in the molecule, which is basically in the oxygen atom, and there will be partially positive charges present on this part of the water molecule for the hydrogen. All right, so we have a net dipole. We have a negative end and a partially positive end. So therefore, the water molecule is polar. Okay. Now, it's not all the time that the if you have a polar bond you will eventually end up with a polar molecule. No, because again the molecular shape has something to do with molecular polarity. So take for example carbon and oxygen. So carbon and oxygen, if you try to look at the bond between the two, oxygen is hungrier for electrons than carbon, so there is actually a dipole moment going towards oxygen. Okay, so this is our first case, and in this part there is another uh, dipole moment going towards the other oxygen atom. Okay, and you know that they are of equal magnitudes because they are the same atom, but they are opposite in direction. So what happens to forces that or to vectors that are equal in magnitude but opposite in direction? They cancel each other out. Okay, so meaning to say there is no net dipole that will be generated. So these two dipoles cancel each other out, especially that the shape of the carbon dioxide molecule is linear. All right, so this is one good example of dipoles canceling each other out. Therefore, carbon dioxide is a non-polar molecule. All right, non-polar molecule. So here is another example of a polar and a non-polar molecule. So you might have noticed that there is a net movement of electrons from this hydrogen towards carbon, since carbon is more electronegative. So if you see that these dipoles point to the same direction, okay, and most of them prevail, so there is a net downward moment. So we consider that molecule to be a polar one. However, if the components of the vectors are canceling each other out, so remember, for each arrow, you can dissect it, resolve it into its x and y components. You remember vector diagrams, okay? So if there are components that are canceling each other out, then the molecule will be nonpolar. Now, I'd like to bring your attention also to the type of atoms being present here. So this is they are almost similar, except that in this molecule we replace the chlorine atom with a hydrogen. Okay, and that will be considered later on. Okay, in this case there is a symmetrical arrangement of dipoles, so they are uh, the same on both sides. So that is also one of the factors that make them nonpolar. Okay, wherein the dipoles cancel each other out because of their symmetrical arrangement. However, in here, we do not have a symmetrical arrangement because there's one different atom, and that spells the difference. That atom spells the difference. All right? So here are a few examples or the types of molecules with polar bonds, okay, but no resulting dipole moment. Okay, so one thing to highlight, just because the bond is polar that is present in a molecule doesn't mean that the molecule will automatically be polar. Okay, I hope you get that. Just because you have a polar bond doesn't automatically mean that your molecule will be uh, polar. It all depends on the dipoles, the arrangement of dipoles, and the molecular geometry. Okay? So here we have a trigonal planar and tetrahedral. So as long as the dipoles cancel out, as long as the polar bonds cancel out, they then we will still have a nonpolar molecule. Okay? So we summarize this one in our notes. Okay, number one, molecules can either be polar or nonpolar, and nonpolar molecules have an even or symmetrical distribution of charge. Okay, an equal distribution of charge. So if all atoms, so this can happen in two cases. The first one is if all atoms are the same in a two atom molecule. So meaning they have the same pull, the same electronegativities, and they are of the same atoms. So there is no resulting net dipole. Okay. The second case is if there are no lone pairs on the central atom and the attached atoms are all the same, just like what we have shown in the two examples a while ago, the CCl4 and the HCCl3. All right. So as long as you have the same types of atoms, the same attached atoms on your structure, then and there are no lone pairs in your leads, then most probably your molecule will be nonpolar. Now, in the case of polar molecules, they have an uneven or asymmetrical distribution of charges. Okay, that means the molecule has a net dipole, meaning it has a partially positive end and a partially negative end. Okay, and it can happen in two cases. Now, the first one is if the outer atoms are different from each other. Okay, just like HCCl3 in the previous example, there is one atom that is different from all the others. And if there are no lone pairs on the central atom, or rather, if there are lone pairs on the central atom, so meaning to say your central atom in your lead structure has a non-bonding pair. There are dots on your central atom. All right, so that practically summarizes. Okay, and we have a few more examples here. Okay, so you can also have nonpolar bonds, nonpolar covalent bonds, which resolve to a nonpolar molecule. So methane is a type of gas. It's used as a fuel. Okay, then we also encountered carbon dioxide, which has a polar covalent, but because of their electron or because of their molecular geometry, carbon dioxide molecules are nonpolar. Okay, so general rules. So you will know if you have a polar molecule if it has, okay, a non-bonding pair or pairs on the central atom, and the dipoles do not cancel each other out, and they have non-identical attached atoms, meaning they have different attached atoms in an asymmetrical arrangement, okay, in an uneven arrangement. So a key principle here is like dissolve like. Okay, uh, maybe in your lower years you've heard of the principle like dissolves like, but it's actually like dissolve like, the proper way of phrasing it. Okay, so that means polar solutes dissolve in polar solvents, and nonpolar solutes will dissolve in nonpolar solvent. Okay, so that's the primary principle why oil and water do not mix. So oil is nonpolar and water is polar. And then we have the principle like dissolves like. So meaning to say, if you identify the polarity of certain substances experimentally, you will know that that substance is polar if it dissolves in water. All right, if it doesn't dissolve in water, then most probably that substance will be non-polar. Okay, but remember that polarity, molecular polarity, have some extents. Okay, so for example, when you talk of dissolving or dissolution, some substances can be partially soluble in water and partially soluble in non-polar substances. So be very careful of that. But in terms of the general trend, okay, this is what we usually use as a guide. Okay, anything that the substances that dissolve in water are generally polar, and the substances that do not dissolve are generally non-polar. All right. So you have here the caricature which I hope will help you in your performance tasks regarding COVID. So this practically explains why we must wash our hands, okay, regularly. So what are we trying to do? What are we trying to have to maximize? Okay, the washing of hands has something to do with polarity. Okay, the polarity maybe of the enclosing proteins on the coronavirus and with water. But how do we get rid, how do we destroy the enclosing proteins? Okay, so I hope this discussion aids you in your capstone activity. And that's it for molecular polarity as we relate it to molecular geometry. All right, so have a nice day, everyone. And then let us take our break now. And thank you so much for your attention.